All right, students, so we're going to do a video on exponential growth. I'd say it's a quick video, but I don't think it's going to be too fast. So there's a lot to talk about with exponential growth. So I thought this was a pretty cool cartoon by this guy Greenberg. Not sure who he is. Anyway, just want to make sure he gets credit. So here we go. Exponential growth. So remember, there the word exponent isn't exponential. So sometimes you'll see the term geometric growth, which we'll talk about, especially when we get to some of the financial applications, or periodic growth. So exponential growth. So we're going to look at this example. We looked at this one in class, I believe. A university currently has 4,000 students. Enrollment is increasing by 5% per year or annually. How many students will enroll in 5 years? So we looked at both recursive equations and general or explicit equations. So the recursive equation here would be, it's just the previous period or the previous year times 1 plus the growth rate, which in this case is 5%. And then each year it's just going to continue to grow by that. So let's take a look. This is the recursive form. So year 1, we're just going to have 4,000. This is like P0, right? This is the starting point. And after year 1, we would have that times 1.05 because 100%. So each year it's going to increase by the growth rate, which is 1 plus 0.05. So think of the 1 as 100% and the 0.05 is 5%. And we talked about that when we looked at percentages way back when. So 100, it would be 4,000 basically plus 5% of 4,000, or we could just multiply that whole thing by 1.05. So each period, it's just going to increase by another 1.05. So I'm just going to multiply by 1.05 each time. So if we think about that, this would be 1.05 to the first power squared, cubed, and then to the fourth power. So I can just rewrite it that way. And then this gives us our general form for the equation. So P in any period, the population of students in any period is just the starting point times 1 plus R to the nth power. So in the 5th year, it would just be 4,000 times 1.05 to the 5th power. I like actually writing it out like this because this shows 1.05 to the 5th power is 1.2763 something 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 expanded. So this shows that after 5 years, the population is actually growing by about 28%. So that's what this number is really showing us. It's the 5-year growth. And that translates to approximately 5,105. So now we're going to actually try and find the growth rate. So that's how you find, say, the population at nth period or at nth years or whatever the time period is or the period is. So if we want to solve for R, this is a little different. So what we're going to do is we're going to use this general form or this explicit form of the equation and see if we can solve for R. And to solve for R, all I'm going to do is just isolate that variable. So if I divide both sides by P sub 0, then that's going to leave me P sub n divided by P sub 0 equals 1 plus R to the nth power. Now, if we remember our power rules, our exponent rules, if I raise this nth power to the 1 over nth power, then a power rule is you multiply the exponents, right? So n times 1 over n is just 1. So that's how I get rid of this n over here. But I have to do that to the other side. So I'm going to raise this p to the n over p to the 0 to the 1 over nth power. Or you could think of it as like the nth radical. So I'm going to go ahead and erase that because that all simplifies. Now I just have to subtract 1 from both sides. And so R is just the final period, whatever that value is, divided by the starting period, raised to the 1 over number of periods minus 1. And that's how we solve for R. And we looked at this with stocks, right? So we looked at Starbucks, I believe. And so we looked at and said, all right, so the current stock price of Starbucks is around $65.34. And 5 years ago is $38.83. So what was the annual growth rate? Well, if this was for 5 years, we can just go ahead and use that calculation we just did. So it would be 65.34 divided by 38.83, raise that to the 1/5 power, and subtract 1. So I can go ahead and plug all that in my calculator. So what I would do is say, 65.34 divided by 38.83 and raise that. I can use this little caret symbol to raise that to the 1/5 power, and then subtract 1. And you'll see it's approximately 11% per year. And so that's the annual growth rate for Starbucks the last 5 years. Pretty amazing growth rate actually for a stock. That's pretty impressive. Okay, so the next thing we're going to see if we can do is solve for the number of periods or number of years or whatever that n is. And that's going to be the complicated thing to solve for in these calculations. So finding p, or p sub n, isn't too bad. Solving for r is a little more complicated, but again, not such a terrible calculation. But if we want to solve for the number of periods, that's a little tricky. So let's say if Starbucks growth continues at 11% per year, when will the stock be worth $1,000? That's what we want to figure out. So if I'm going to invest in Starbucks, now 11% growth over the next however many years is kind of unreasonable to expect, but when would the stock be worth $1,000 in that case? Or this is really good for like if you're doing interest rate calculations, because interest rates are generally fixed, or a lot of times they're fixed, and so you can actually forecast out for say 30 years how much interest you're going to pay for something, and you can figure out like how much you're going to owe at the end of the time. So let's go ahead. We can graph this. So what I'm going to do to solve it graphically, I was just going to plot this horizontal line, y equals 1,000, because that's where I want, that's my target. And then I'm going to go ahead and plug in this other thing here, which is just 65. That's my starting stock price. That's the stock price today is about $65. And it's going to grow at 1.11 or 11% per year, right? For X number of years. And then so I can just go ahead and graph that. And let's take a look. Before I graph it, what I really need to do is fix the window, right? So I'm going to set my window to like say -10 for X, and then 30. I'm just going to assume it's going to go out, maybe 30 years like this way. And then I'm going to set the Y minimum at -10, and then I need to go over 1,000, right? It's going to go over 1,000 this way, so I want to make sure I set my window to say 1,500 or something. So when I plot that, and I was using Graphing Calc on my iPad to do this. It's a really, really nice graphing calculator, and you can just click on the intersection. You don't even have to do that second calc, which you could do on the other graphing calculator, the TI-84, and calculate the intersection. But you don't have to do that on this one. You can just click where you want to see the intersection. So here's the intersection, and it tells me that the X is about 26 years. It's 26.2 years. So it's going to take 26 years for me to reach $1,000 for a share price of Starbucks. So how do we do this not graphically? That's the real trick. And so here, if we want to figure out this graph is just continuing on, right, at that 11% growth rate. So you can figure out like 5 years ago is here, and it's kind of just continuing on at that exponential rate. Or this would be called geometric growth because it's kind of going at each period, and we're going to talk more about that later in the course. How do we solve for that mathematically without graphing it? Well, you have to use logs. So I know you all are familiar with logs. We did logs in Algebra 2, and some of you have taken calculus, and I know you've done logs in calculus. So to solve an exponential equation for the exponent, remember log is an exponent. Basically, logs are actually undoing the exponent, so it's an inverse operation. So like division is the inverse operation of multiplication, or subtraction is the inverse operation of addition. Logs are just the inverse operation of exponents. So if p sub n is 1,000, that's what my target is, and my starting point is 65, and the growth rate is 0.11, I can go ahead and write that out. So 1,000 equals 65 times 1.11 to the nth power, but I want to solve for n. So to do that, I need to take the log of both sides. Well, first I could divide both sides by 65. And then what I'm going to do is take the log of both sides. So I divided both sides by 65, and that gave me 1,000 over 65 equals 1.11 to the nth power. And then if I take the log of both sides, that leaves me with log of 1,000 over 65. And remember, log with no base down here assumes it's base of 10. So that's log base 10. So this is just a general log. And then I can rewrite the log of 1.11 to the nth power as n times log 1.11. That's our power rule or exponent rule for logs. And we can just plug this right into our calculators. Well, first of all, I need to divide both sides by log of 1.11. And then I can plug that into my calculator because n equals this whole mess on the left. So that's what I did. I just plugged it into my calculator over here. Up here at the top, I just plugged in exactly that. Log of 1,000 divided by 65 divided by the log of 1.11. And I get 26.1917, which is exactly what I got here graphically. So the other thing I wanted to show you is, remember our log rules. So the log of 1,000 divided by the log of 65, the log of 1,000 divided by 65, we can rewrite as log of 1,000 minus log of 65. So remember, if you're dividing a fraction, if you have some sort of fraction here, it's just log of 1,000 minus log of 65. That was our log rules for that. All right, so those are two ways to do it on the calculator. I hope this helps. Please let me know if you have any questions, and maybe I'll make another video on logs. Thanks for watching.